Take a neutron out of an atom, set it down alone, and start a clock. In about 15 minutes, it will be gone. Not moved, not hidden, but transformed into other particles, as if it carried an expiration date written into nature. And yet the same neutron, locked inside a nucleus, can sit unchanged for longer than the universe has existed. One is doomed. The other is immortal. They are identical. Tonight we follow a lonely neutron through its brief life, into the strange reason it cannot survive alone, and into an unsolved mystery hidden in those minutes. Stay a while. A like and a subscribe help. Tell me, where are you watching from, and what time is it there? Picture a single neutron floating alone in empty space. It is one of the most ordinary things in the universe. There are neutrons inside almost every atom in your body, inside the chair you are sitting in, inside the walls and the ground and the distant stars. They are one of the two main ingredients of all ordinary matter, the quiet partners of protons in the hearts of atoms. You are, in a very real sense, partly made of neutrons. They feel about as permanent and as solid as anything could be. And yet, this one, floating alone, is dying, not metaphorically, not slowly wearing down, actually dying on a clock you could measure with a stopwatch. If you could pluck a single neutron out of an atom and set it down by itself in the vacuum, and then simply wait and watch, you would find that in about 15 minutes on average, it would be gone. In its place would be other particles entirely. The neutron would have transformed itself spontaneously into something else, with no warning and no cause that you could point to from the outside. One moment a neutron, a little later not. Let that sit for a moment, because it is genuinely strange. We tend to think of the basic building blocks of matter as eternal. A proton, as far as we can tell, lasts essentially forever, longer than the age of the universe by an almost unimaginable margin. An electron is stable. The atoms in your body have been around in one form or another since long before the Earth existed. Permanence is what we expect from the fundamental pieces of reality. And here is one of the most common particles there is, a piece of nearly every atom heavier than simple hydrogen, and on its own it cannot last a quarter of an hour. It carries something like a deadline written into the deepest laws of physics, a countdown that begins the moment it finds itself alone. This is the puzzle we are going to sit inside tonight. Not rush through, sit inside, because it turns out that the short life of a lonely neutron opens a door onto some of the most beautiful ideas in all of physics, and also onto a genuine, unsolved mystery that real scientists are arguing about right now, today, with no agreed answer. We are going to follow a single neutron from the moment it is set free, through its brief life, to the instant it transforms, and then deeper into why it must do this when alone, and why, astonishingly, it does not have to when it has company. And along the way we will arrive at a place where two of the most careful experiments ever performed flatly disagree with each other by an amount that should not be possible, and nobody yet knows why. So let us begin gently, with the particle itself, because to feel the strangeness of its death, you first have to feel the ordinariness of its life. A neutron is a subatomic particle, one of the constituents of the atomic nucleus, the dense little knot at the center of every atom. The nucleus is built from protons and neutrons packed tightly together, and around it, far away in the atom's outer reaches, the electrons drift. The protons carry a positive electric charge. The neutrons, as their name suggests, are neutral, carrying no charge at all. They are very slightly heavier than protons, but otherwise the two are close partners, similar in size and in mass, sitting side by side in the nucleus, and together they account for nearly all the mass of every atom, and so nearly all the mass of everything you have ever touched. The number of protons in the nucleus decides what element the atom is. 1 proton makes hydrogen, 2 makes helium, 6 makes carbon, 8 oxygen, and so on up the periodic table. But the neutrons matter too. They add mass and they help hold the nucleus together, and the number of them can vary, giving different versions of the same element, which we call isotopes. Most of the matter around you depends on neutrons being there, quietly doing their part, holding the heavier nuclei together. Without them, there would be no carbon, no oxygen, no iron, no gold. There would be little more than hydrogen, the simplest atom, a single proton with a single electron, and a universe of almost nothing else. Neutrons are, in a real sense, part of why there is interesting matter at all. So where would you even find a neutron on its own? This is worth pausing on, because in everyday life you never do. Neutrons are almost always locked away inside nuclei, bound up with protons, doing their quiet work. To get a free one, you have to break it loose, and that takes violence at the nuclear scale. Free neutrons are released in certain nuclear reactions. They pour out of the cores of nuclear reactors where heavy atoms are splitting apart. They are flung out in the fusion reactions at the hearts of stars and in the explosions of stars. They are produced when cosmic rays, high energy particles from space, slam into atoms in the upper atmosphere, and we make them deliberately in laboratories, in research reactors and special facilities built precisely so that physicists can catch free neutrons and study them. So free neutrons are real, and they are all around in certain places, but they are always fleeting, always recently, broken loose, always from the moment of their freedom on the clock. And here is the number, stated carefully, because the exact value is going to become the heart of our mystery later. A free neutron on its own has an average lifetime of roughly 15 minutes. More precisely, its mean lifetime is about 880 seconds, which is 14.5 minutes or so. Now, average is an important word here, and it works the way it does for radioactive decay generally. It does not mean every neutron lasts exactly 15 minutes and then drops dead on schedule. It means that decay is a matter of probability. Any given neutron might transform in the first second or it might last half an hour. But if you watch a great many of them, half of them will be gone after about 10 minutes, and the average survival time works out to around 15. It is like popcorn in hot oil. You cannot say when any single kernel will pop, but you know the rhythm of the whole batch, and you know that before long the popping will be done. There is something almost poignant in that, if you let yourself feel it. A free neutron does not age. It does not get tired or wear out. At any instant, a neutron that has already lasted 14 minutes is exactly as likely to survive the next second as one that was freed a moment ago. There is no memory, no accumulation of damage, no slow decline. There is only, at every moment, the same small chance of sudden transformation hanging over the particle from the instant it is alone. It lives, you might say, entirely in the present, carrying the same quiet probability of vanishing in every passing second until the second comes when it does. It is worth knowing how recently we even learned that the neutron exists, because it reminds us how hidden this particle is. The neutron was not discovered until the early 1930s, much later than the proton and the electron. And the reason is precisely its neutrality. Because it carries no electric charge, a neutron does not announce itself the way charged particles do. It does not curve in an electric field. It does not leave the kind of clear trail that charged particles leave in detectors. It slips through matter quietly, invisibly, interacting only when it happens to strike a nucleus, directly. For a long time, physicists suspected something like it had to be there, because the masses of atoms did not add up if nuclei were made of protons alone. But proving it took careful, clever experiments, watching for the faint secondary effects of a particle that refused to be seen directly. The neutron was the hidden partner, the neutral one, the piece that had been holding the nucleus together all along while staying out of sight. And once we knew it was there, we slowly learned its strange habit. A neutron locked in a nucleus might last forever, but a neutron set free was unstable, and its instability had a name we already knew from another context. It is radioactivity. The decay of a free neutron is, in fact, one of the simplest and purest examples of radioactive decay in all of nature. When you hear the word radioactivity, you may think of uranium, of nuclear reactors, of glowing danger. But at its heart, radioactivity is just this: certain particles and certain nuclei spontaneously transforming into other things because they are carrying a little more energy than they strictly need to, and the universe permits them to shed it. The low neutron is radioactivity stripped down to its barest essence, a single particle all by itself, undergoing the same fundamental kind of transformation that powers the decay of the heaviest elements. To understand the neutron is to understand radioactivity in its simplest possible form. Let me give you a feeling for the scale of the thing we are discussing, because it is easy to lose track of how unimaginably small a neutron is. An atom is already far too small to see. You could line up millions of them across the width of a human hair. And the nucleus, where the neutrons live, is 100,000 times smaller than the atom itself. If an atom were blown up to the size of a large stadium, the nucleus at its center would be no bigger than a small pea on the center spot, with the rest of the stadium nearly empty. The neutron is one component of that pea. It is a speck within a speck within a speck, a thing so small that the word small stops meaning anything useful, and this almost infinitely tiny object, this fleck of matter at the very bottom of the scale of things, carries within it a precise and reliable clock, a countdown measured in minutes, governed by the deepest laws of physics. There is something humbling in that the universe should write such exact rules into something so impossibly small. How do we even know that free neutrons decay in about 15 minutes, given that we cannot watch a single one? We do it the way we do all of this kind of science, with great numbers and great care. You cannot follow one neutron and time its death with a stopwatch any more than you can predict which popcorn kernel pops first. But you can take an enormous population of free neutrons and watch the whole crowd and measure how quickly they thin out. You can count how many are left after a known stretch of time. Or you can count the particles that appear as they decay, and from the rhythm of the whole population, you can extract the average lifetime with remarkable precision. This is exactly what physicists have spent decades doing, building ever more careful experiments to pin down that number, the mean life of a free neutron, to better and better accuracy. And as we will see, it is in the fine details of those measurements, in the chase after the last fraction of a percent, that the real mystery of this whole story is hiding. The 15 minutes are not just a curiosity. They are a number that physicists have been trying to nail down exactly for a very long time. And the closer they look, the stranger the situation becomes. But all of that is ahead of us. For now, simply hold the basic, astonishing fact in your mind. A neutron is one of the fundamental pieces of ordinary matter. It is in nearly every atom heavier than hydrogen. It is in you, and on its own, cut loose from the nucleus, it survives only about a quarter of an hour before transforming into other particles entirely. It does not wear out, it does not age, it simply carries every second of its lonely existence, the same small chance of sudden change until the change comes. Now hold that picture, the lone neutron with its even, memoryless countdown, and set beside it the fact that turns this from a curiosity into a genuine riddle. The neutrons inside the nucleus of an ordinary atom do not do this. The neutrons in the carbon of your bones, in the oxygen of the air, in the iron at the Earth's core, have been sitting there, stable and unchanging, for billions of years. The carbon in your body contains neutrons that have not decayed since they were forged inside an ancient star long before the sun was born, and they show no sign of decaying anytime soon, bound inside a stable nucleus. A neutron is, for all practical purposes, immortal. It can outlast worlds. So we have two neutrons. They are utterly identical. There is no inner difference. Between them, no hidden variation, no mark that distinguishes one from the other. Take the immortal neutron out of its nucleus, set it loose, and within 15 minutes it will die. Take the dying free neutron and lock it into the right nucleus, and it will last longer than the universe has so far existed. The same particle, two completely different fates, and the only thing that has changed is whether it is alone or not. How can that be? How can being part of a group make a particle immortal while being alone dooms it? What is it about the company of other particles that holds back a transformation that, in solitude, is unstoppable? And what exactly is this transformation in the first place? This quiet vanishing that turns a neutron into something else? These are the questions we are going to follow carefully, one at a time. The answer reaches down into the very nature of mass and energy, into a force so subtle it is called simply the weak force, and into the strange accounting by which the universe decides what is allowed to happen and what is not, because that, in the end, is what a neutron's death really is. Not destruction, not a thing, breaking. It is the universe enforcing a rule about energy, a rule that says certain things are allowed to fall to lower states when nothing holds them up, and that a lone neutron is perpetually poised at the top of a tiny hill, free to roll down the moment it is left, unsupported. Inside a nucleus, something holds it on the hilltop. Alone, nothing does, and so it falls. And this is not a small or academic question, though it begins with the tiniest of objects. The exact length of those 15 minutes turns out to be woven into the history of the entire universe. In the first minutes after the Big Bang, when all of existence was a hot, dense soup of particles, free neutrons were everywhere, and they were racing against their own clocks. Whether a given neutron survived long enough to be caught up and bound into a nucleus, or decayed first while still alone, helped decide how much of the early universe became helium and how much stayed as simple hydrogen. The balance of the elements, the raw material from which every star and planet and living thing would later be built, depended in part on this one number, the lifetime of a lonely neutron. So when we ask why a neutron cannot survive on its own, and exactly how long it lasts, we are not asking a trivial question about an obscure particle. We are asking a question whose answer is written into the composition of everything. We will return to that cosmic story at the very end. Once we understand the particle itself, I mention it now only so you can feel that the stakes of this little 15-minute clock are quietly enormous. There is also a quieter thread running underneath all of this, one I want to plant now so it can grow as we go. We tend to imagine that things are either stable or unstable by their own nature. That permanence is a property a thing simply has or lacks. The neutron tells us otherwise. The very same particle is permanent in one setting and doomed in another, and nothing about the particle itself has changed. Its fate is decided not by what it is, but by where it is, by what surrounds it, by the company it keeps. Stability, the neutron whispers, is not a possession, it is a relationship, and that turns out to be true far beyond this one particle, true in ways that reach all the way up to stars and perhaps to us. But we are getting ahead of ourselves. Hold the thought lightly, it will return. Let us take a slow breath and begin the descent into why. We start with the deepest and simplest idea of all, the one that decides the fate of every particle in existence. Not force, not motion, energy. And the strange truth that a neutron, sitting perfectly still, is already carrying just a little too much of it. To understand why a lone neutron dies, we have to understand the single deepest rule that governs what is allowed to happen in the universe. It is not a rule about force or motion or even time. It is a rule about energy, and it can be stated very simply. Left to themselves, things tend to fall toward lower energy. You already know this rule in your bones because you live inside it every day. A ball at the top of a hill rolls down, not up. Water flows downhill, not up. Heat spreads from the hot thing to the cold thing, evening out. A stretched spring snaps back. Everything, when nothing holds it in place, tends to move toward a state of lower energy, releasing the difference along the way. A ball on a hilltop carries extra energy by virtue of its height, and given any chance, it will give that energy up and roll to the bottom. This is one of the most reliable patterns in all of nature. High energy states are restless. They want to fall. And if there is a lower energy state available and a path to reach it, sooner or later the fall happens. Now here is the move that unlocks everything. In the world of particles, this same rule holds, but with a twist that comes from the most famous equation in all of science. Mass and energy are the same thing. They are interchangeable, related by Einstein's equivalence, the idea that a given amount of mass is equivalent to a certain amount of energy, and the conversion factor is enormous. This means that the mass of a particle is not just a measure of how much stuff it contains. It is a form of energy. A heavier particle carries more energy locked up in its very mass than a lighter one. And so the rule that things fall toward lower energy becomes, for particles, a rule that can be paid in mass itself. A heavier particle can, under the right conditions, transform into lighter particles, and the difference in mass is released as energy, as motion, as other particles flying away. The heavy thing falls to the light thing, and the missing mass becomes the energy of the fall. So the question of whether a particle can decay becomes a question of simple bookkeeping. Add up the mass of the original particle, add up the mass of the particles it might turn into. If the original is heavier than the sum of the products, then decay is allowed, because the particle can fall to a lower energy state and release the difference. If the original is lighter, then decay is forbidden, because it would require creating energy out of nothing, and that the universe does not permit. It really is that simple, at the most basic level. Can this thing become lighter things? If yes, and if there is a path, it eventually will. If no, it is stable, frozen in place by the iron law that energy cannot be conjured from nowhere. Now let us weigh our neutron. Here is the crucial fact, and it is a close thing, a matter of the finest margin. A neutron is very slightly heavier than a proton, just a little. And when a neutron decays, it becomes a proton plus an electron plus one more very light particle. We will meet properly soon. Add up the masses of that proton and that electron and the third tiny particle, and the total comes out just a hair less than the mass of the original neutron, just barely less. The neutron sits a tiny step above the combined weight of the things it would become, which means, by the rule of energy bookkeeping, the neutron is allowed to decay. It is ever so slightly too heavy. It is carrying just a little more mass, and therefore just a little more energy than the particles it could fall into. It is a ball resting at the top of a very shallow hill with a lower state just below it and a path leading down, and so, given the chance, it falls. That is the death of a free neutron. It is a ball rolling down a tiny hill. It is a slightly too heavy particle shedding its excess by transforming into slightly lighter ones, releasing the small difference as energy. There is no villain, no force reaching in to destroy it, no decay in the sense of rot. There is only the universe doing what it always does, letting a high energy state fall to a lower one when nothing stands in the way. The neutron decays for the same fundamental reason that water runs downhill. It can, and so it does. Let us appreciate how delicate this balance is, because the whole story turns on it. The difference in mass between a neutron and the particles it becomes is astonishingly small, a tiny fraction of the neutron's total mass, well under 1 part in 1,000. If the neutron were just a little lighter than the proton and electron combined, it could not decay at all, and a free neutron would be as stable as a proton, lasting forever. The universe would be a profoundly different place, and if the neutron were much heavier, the hill would be steeper, the fall faster, and free neutrons would vanish almost instantly, rather than lingering for 15 minutes. The neutron sits in a delicate sweet spot, heavier than its decay products by just the barest sliver, and that tiny sliver is exactly what gives it its strange, fragile 15-minute life. The whole drama hangs on a difference of weight so small you could almost call it nothing. Let us linger on the idea that mass is energy, because it is so central and so easy to nod along to without really feeling. We are used to thinking of mass as how much matter there is, a measure of substance, of heft, and we are used to thinking of energy as something separate, the capacity to do work, the thing that makes engines run and lights glow. Einstein's great insight was that these are not two different things, but two faces of the same thing. Mass is a kind of frozen, concentrated energy, locked into the very existence of a particle. The proof of this is all around us. It is why the sun shines, converting a tiny fraction of its mass into the energy that warms the earth. It is why Nuclear reactions release such enormous power because they convert mass into energy at that vast exchange rate. And it is why a slightly heavier particle can transform into slightly lighter ones and release energy in the process. The extra mass of the neutron is not just dead weight. It is fuel. It is the energy of the fall, waiting to be spent. So when a free neutron decays, where does that little bit of extra energy actually go? Does not vanish. The universe keeps strict accounts. The small surplus of mass, the difference between the neutron and its products, is released as motion. The new particles fly apart, carrying the freed energy as their speed and momentum. The electron in particular is flung out with a share of the energy, sometimes a little, sometimes more, and it can be detected as a tiny burst of what physicists historically called beta radiation. So the death of a neutron is not silent or invisible. It produces a faint flash of flying particles, a small spray of energy and motion, the release difference of that delicate margin of mass, scattering outward into the world. Every decaying neutron pays out its tiny surplus, and that payout is exactly what our detectors catch. When we study these transformations, it is worth being precise, gently, about the timing words too, because they matter when we reach the mystery. I have been saying a free neutron lives about 15 minutes on average, and that is the mean lifetime, the average survival time across a whole population. There is a related number called the half-life, which is the time it takes for half of a large batch of neutrons to decay, and for the neutron that works out to around 10 minutes. Both numbers describe the same underlying process, just measured in slightly different ways. The way you could describe the same fading sound by how long until it is half as loud, or by its average duration. The mean lifetime of roughly 880 seconds is the figure physicists most often quote, and it is the precise value of that number, hunted to the last fraction of a second, that will become the center of the unsolved puzzle waiting for us later. For now, just hold the rough picture. A free neutron, left alone, has a bit more than even odds of surviving the first 10 minutes, and on average lasts about 15, before it spends its small surplus of mass and transforms. And one more thing is worth noticing about that surplus, because it deepens the sense of how finely balanced the neutron is. The neutron and the proton are, at a deeper level, each built from still smaller particles called quarks, and the tiny difference in mass between a neutron and a proton traces back to a tiny difference in the quarks inside them. The neutron contains a particular heavier kind of quark, where the proton contains a lighter kind. And that minute difference at the level of the quarks is what makes the neutron just barely heavier, overall just barely able to fall. So the whole drama of the neutron's fragile life, its 15-minute clock, its inability to survive alone, traces all the way down to a sliver of mass difference between two kinds of quark buried inside it. The fate of the particle is decided in its smallest depths. We will open up the neutron and look at those quarks directly in a little while. because the transformation of one quark into another is the true engine of the whole process. But now we come to the heart of the riddle, the thing we have been circling since the prime beginning. If a free neutron decays because it is slightly too heavy, then why does a neutron inside a nucleus not decay? It is the same particle. It has the same mass. By the bookkeeping we just laid out, it too should be too heavy, should also want to fall. And yet the neutrons in stable atoms last forever. What changes when a neutron has company? The answer is that the bookkeeping is not done on the neutron alone. It is done on the whole system. And inside a nucleus, the neutron is not a separate thing sitting by itself. It is part of a bound community of protons and neutrons, all held together, all sharing in a deep pool of binding energy. When you ask whether a bound neutron can decay, you cannot just weigh the neutron and its products in isolation. You have to weigh the entire nucleus before, and the entire nucleus after, including all the rearrangement that the decay would cause. And here is the key. In a stable nucleus, the arrangement is already so finely tuned, the binding so deep that turning one of its neutrons into a proton would actually produce a heavier overall system, not a lighter one. The would-be result sits higher in energy, not lower, and the rule is absolute. Things do not spontaneously climb to higher energy, so the decay simply cannot happen. The neutron is forbidden from falling, not because anything reaches in to hold it, but because there is no lower place for it to fall to. The hill for a bound neutron in a stable nucleus runs uphill in every direction. Feel the elegance of that. The free neutron sits at the top of a tiny hill with a valley just below, and it rolls down. The bound neutron in a stable nucleus sits at the bottom of a par valley already, with walls rising on every side, and so it stays. Same particle, same mass. But the landscape of energy around it is completely different because of the company it keeps. Alone there is a way down, together there is not. The neutron's fate is decided entirely by the shape of the energy landscape it finds itself in, and that landscape is set by its surroundings. Let me make that energy landscape more vivid, because it is the single most important idea for understanding the neutron's two fates. Imagine a hilly landscape with peaks and valleys, and imagine that every possible arrangement of particles is a place somewhere on that landscape, higher up if it carries more energy, lower down if it carries less. A free neutron sits on a gentle rise, with the slightly lower ground of a proton and electron just below it, and a path leading down. Release it, and it rolls into that lower ground. Simple. Now imagine the same neutron, but bound into a stable nucleus. The whole nucleus occupies a deep valley in the landscape, a place of unusually low energy, which is exactly what it means to be tightly bound. To turn one of its neutrons into a proton, the nucleus would have to move to a different spot on the landscape, the spot representing the new arrangement. And for a stable nucleus, that new spot is uphill. The would-be product sits higher, not lower. So the move is forbidden, because nothing rolls uphill on its own. The bound neutron is trapped in the valley, not by chains, but by the simple fact that every direction out of the valley leads up. This is why I keep saying the neutron's fate depends on its surroundings rather than on itself. The particle is identical in both cases. What differs is the shape of the landscape around it, which is set entirely by its neighbors and the binding they share. In open space, alone, the landscape tilts downhill toward decay. Inside a stable nucleus, the landscape tilts uphill in every direction, and the neutron is safe. The neutron does not know or care which situation it is in. It simply obeys the same rule in both. The rule that says, fall if you can. In one place it can, in the other it cannot. And that difference between can and cannot is the entire difference between a 15-minute life and an eternity. There is a beautiful subtlety hidden here that is worth drawing out. The binding energy that makes a nucleus stable, that digs the deep valley, is itself a kind of negative energy, an energy debt that has been paid to hold the particles together. When protons and neutrons come together into a tightly bound nucleus, they actually release energy in the process. And so the bound system weighs slightly less than the same particles would weigh separately. The bound nucleus is lighter than the sum of its parts, and that missing mass is the binding energy, the depth of the valley. It is precisely this missing mass, this discount on the total weight, that can make decay unprofitable. If turning a bound neutron into a proton would land the nucleus in a configuration whose total mass is higher, the decay cannot pay for itself, and it does not happen. The whole stability of matter, the permanence of the atoms in your body, rests on this quiet accounting of mass and binding, valley by valley, across the whole landscape of possible nuclei. This is the first deep answer to our riddle, and it is worth sitting with before we go further. A neutron cannot exist alone because, alone, it is slightly too heavy, perched just above a lower energy state, free to fall. It can exist inside a nucleus because there, the act of falling would mean climbing, and climbing is forbidden. Stability is not a property the neutron carries within itself. It is a property of the whole arrangement of the balance of energy across the entire bound system. The neutron is permanent, doomed, depending on the energy landscape its neighbors create around it. Notice, too, how much we have already explained with nothing more than the single rule that things fall toward lower energy, paid in the currency of mass. We have not needed anything exotic. We have not invoked any mysterious force reaching in to kill the neutron or to protect it. We have only weighed things before and after and asked whether the after is lighter than the before. That one question, asked honestly, tells us whether any transformation in the universe is allowed. It is one of the most powerful and most general ideas in all of physics, and the humble neutron is one of its purest illustrations. Hold on to that clarity, because the next layer of the story, the actual machinery of the decay, is stranger and more surprising, and it helps to carry a clear principle with you into stranger territory. But we have left two things unexplained, and they are the next steps of our descent. First, what actually happens during the decay itself? We have said the neutron becomes a proton and an electron and a third small particle, but we have not yet looked at the strange machinery of that transformation, the force that drives it, the ghostly particle that escapes, the deep change happening inside the neutron at the level of its smallest parts. And second, we have glossed over an important complication in the story of nuclear stability, which is that not all nuclei are stable, that some of them do decay, that the rule is subtler than nuclei, always saving their neutrons. We will take both of these in turn. But first, let us go inside the moment of decay itself and watch, in slow motion, a neutron transform, because the mechanism is one of the most beautiful and surprising things in all of physics, and it introduces a force unlike any other, a force whose only job is to change one kind of particle into another. Let us slow time down, all the way down, and watch a single free neutron in the moment of its transformation. We have said it becomes a proton, an electron, and a third faint particle. Now let us see how that actually happens, because the mechanism is one of the deepest and most surprising things in all of physics, and it forces us to meet a force most people have never heard of, a force whose entire purpose is to change one kind of particle into another. First, we have to open the neutron up, because it is not the smallest thing in the story. For a long time we thought protons and neutrons were fundamental, indivisible, the true bottom of matter, but they are not. Each of them is built from still smaller particles called quarks, 3 of them bound tightly together inside. And there are different kinds of quark. The 2 that matter for us are called by a charming convention with no deeper meaning, the up quark and the down quark. The up quark carries a certain positive electric charge, 2/3 of the basic unit. The down quark carries a negative charge, 1/3 of the basic unit. And the difference between a proton and a neutron at this deepest level comes down entirely to the mix of these 2 kinds of quark. A proton is made of 2 up quarks and 1 down quark. Add up their charges, 2/3 plus 2/3 minus 1/3, and you get exactly 1 positive unit of charge, which is the charge of the proton. A neutron is made of 1 up quark and 2 down quarks. Add up those charges, 2/3 minus 1/3 minus 1/3, and you get exactly 0, which is why the neutron is neutral. So the only difference between a proton and a neutron, the whole difference, is that one of the 3 quarks is swapped. Change 1 down quark in a neutron into an up quark, and the neutron becomes a proton. That is the entire transformation at its core. A single quark changes its identity, and that is exactly what happens when a neutron decays. Deep inside it, one of its 2 down quark suddenly transforms into an up quark. In that instant, the particle that was a neutron with its 1 up and 2 down quarks becomes a particle with 2 up and 1 down, which is a proton. The neutron has become a proton from the inside out by the flip of a single quark. But that flip cannot happen for free, and it cannot happen quietly, because it changes the electric charge of the system, and charge, like energy, must be carefully accounted for. The down quark had a negative charge. The up quark has a positive charge. Something has to balance the books, and the way the universe balances them is through one of the most remarkable processes in nature. When the down quark flips to an up quark, it emits a particle, a heavy and extremely short-lived force carrier called a W boson. This W boson is the messenger of a force we have not yet named, the weak nuclear force, and it carries away the negative charge that has to be shed. But the W boson is itself enormously heavy, far heavier than the neutron that produced it, which sounds impossible, and in a sense it is. It exists only for the most fleeting instant, borrowed from the universe on credit, allowed to exist for a span so short that it can never be directly seen, and almost immediately it decays in turn, transforming into 2 particles that fly out into the world, an electron, which carries away the negative charge, and an antineutrino, the faint ghostly partner that balances the rest of the bookkeeping. So now we can see the full picture of the death of a neutron in sequence. A down quark inside the neutron flips into an up quark, turning the neutron into a proton. In doing so, it emits a fleeting heavy W boson. The W boson, living for less than an instant, transforms into an electron and an antineutrino, which shoot away. What is left behind is a proton. What flies off is an electron and an antineutrino. And the small surplus of energy, that delicate sliver of extra mass the neutron was carrying, becomes the motion of all these departing particles. That is beta decay. That is what a neutron does when it dies. One quark changes its mind, and the whole particle is transformed. I want to dwell on the force behind this, the weak nuclear force, because it is genuinely strange and genuinely underappreciated. We know about gravity, which pulls things together. We know about electromagnetism, which makes magnets stick and lightning flash and holds electrons to atoms. There is the strong nuclear force, which we will meet properly soon, which glues the nucleus together. And then there is this fourth force, the weak force, which is unlike all the others in a profound way. The other forces mostly push and pull. They move things around, attract and repel, hold together and drive, part. But the weak force does something none of the others can do. It changes what particles are. It can take one kind of quark and turn it into another. It can transmute identity itself. It is the only force in nature with the power to change a particle from one type into a fundamentally different type. Without it, a down quark could never become an up quark. A neutron could never become a proton. and the kind of transformation we call radioactive decay could not happen at all. The weak force is also, as its name suggests, weak, and more than that, it has an extraordinarily short reach and acts only rarely. This is actually why a free neutron lasts as long as it does. The flip of a quark through the weak force is not an easy or a frequent event. It is a rare, improbable occurrence, and the neutron has to wait, on average, about 15 minutes for it to happen, even though the lower energy state is sitting right there, available. If the weak force were stronger, the neutron would decay almost instantly. Because it is so feeble, the neutron lingers. Its strange 15-minute life is, in a sense, a direct measure of just how weak the weak force is. The clock of the dying neutron is set by the rarity of that single quark flip. We are watching, in those 15 minutes, the slowness of the only force that can change one thing into another. Now, let us turn to the ghostliest part of the whole story, the third particle, the antineutrino, because its history is one of the most beautiful detective stories in the history of science. When physicists first studied beta decay, before they understood quarks or W bosons, they could see a neutron turning into a proton and an electron, and they ran into a disturbing problem. The energy did not add up. When they carefully measured the energy carried away by the electrons, they found it varied, and crucially, it was usually less than it should have been. Energy seemed to be going missing. Some of it was simply disappearing, unaccounted for, and the same seemed to be true of other quantities that are supposed to be strictly conserved, like momentum and a property called spin. The books would not balance, and the conservation of energy is one of the most sacred principles in all of physics, a law that had never been known to fail. The situation was so serious that some great physicists wondered, briefly, whether energy conservation itself might break down inside the atom. But one of them proposed a bolder and, as it turned out, correct idea. Perhaps the energy was not disappearing at all. Perhaps it was being carried away by a particle nobody could see, a particle with no electric charge, so it left no trail. A particle with almost no mass, and one that barely interacted with anything at all. So it could pass through detectors, through walls, through the entire Earth, without leaving a trace. If such a ghost particle existed and slipped away unseen from every beta decay, carrying off the missing energy, then the books would balance after all. It was a daring proposal to invent an invisible particle simply to save a cherished law. But it was the right call. That ghost particle is the neutrino, or more precisely in this case, the antineutrino, and it took decades to finally catch one directly, because it interacts so rarely with matter that detecting it is fiendishly difficult. Trillions upon trillions of neutrinos are streaming through your body every second, from the sun, from the earth, from the cosmos, and almost none of them touch you at all. They pass through you as if you were not there, as if you were empty space, which to a neutrino you very nearly are, and yet they are real. and they were predicted into existence purely to balance the energy of beta decay, and later found exactly where the theory said they would be. The death of a neutron always releases one of these ghosts, flitting away with its share of the energy, almost never to be seen again. Every decaying neutron sends a tiny, invisible messenger out into the universe, and that messenger almost certainly never interacts with anything, ever again. Let us pause on the strangeness of that heavy W boson, because it touches something profound about how the quantum world works. I said it is far heavier than the neutron that produces it, and that this sounds impossible. It is worth understanding why it is allowed. In the quantum world, energy can be borrowed briefly, as long as it is paid back almost immediately. The shorter the loan, the larger the amount that can be borrowed. So a particle as heavy as the W boson can flicker into existence inside the decay, borrowing far more energy than the neutron actually has, but only for an almost inconceivably brief instant before it must vanish again by transforming into the lighter electron and antineutrino. This is why the W boson is called a virtual particle in this context. It is never really there to be caught. It is a fleeting intermediary, a momentary bridge across which the transformation happens, existing on borrowed time and repaying the loan before the universe can notice. The neutron decay happens through this ghostly heavy messenger that can never quite be said to have fully existed. For decades, the W boson was only a theoretical necessity, a piece the equations demanded but no one had seen. It was finally produced and detected directly in the early 1980s in a great particle collider, by smashing particles together hard, enough to bring real W bosons fleetingly into being, massive and immediately decaying, exactly as the theory of the weak force had predicted. It was one of the triumphs of modern physics, the confirmation that the force-changing quarks inside decaying neutrons was carried by these heavy messengers. So, the quiet death of a lone neutron, happening invisibly in empty space, runs on the very same machinery that physicists later recreated with enormous machines, the heaviest force carriers in everyday matter, summoned for an instant inside the tiniest of particles. There is another deeply strange feature of the weak force worth sharing, because it overturned something physicists had believed was a basic symmetry of nature. The weak force, the one that drives beta decay, turns out to be lopsided. It treats left and right differently. Before the 1950s, everyone assumed that the laws of physics could not tell left from right, that a process and its mirror image would always be equally likely, the way most of physics is perfectly even-handed about direction. But beta decay broke that assumption. When physicists watched the electrons flung out by decaying nuclei, they found that the electrons preferred to come out in a particular direction relative to the spin of the nucleus, a direction that would look different in a mirror. The weak force, alone among the forces, has a handedness. It distinguishes our world from its mirror reflection. This discovery stunned physicists because it meant the universe, at its deepest level, is not perfectly symmetric between left and right. The decay of a neutron, that humble 15-minute event, is tangled up with one of the most surprising asymmetries in all of nature, a built-in preference for one-handedness over the other, woven into the only force that can change one particle into another. Now, let me return to the neutrino, the ghost, and give it the attention it deserves, because it is one of the most haunting objects in physics. We said it was invented to save the conservation of energy, a particle proposed almost reluctantly to balance the books, and later found to be real. But consider what kind of thing it is. It has no electric charge, so the electromagnetic force ignores it. It has almost no mass, and it feels only the weak force and gravity, both of which are, for a single tiny particle, almost negligibly faint. The result is a particle that interacts with ordinary matter so rarely that it is almost not there at all. To stop a typical neutrino reliably, you would need a wall of solid lead, light years thick. They stream out of the sun in unimaginable numbers and pour through the earth as though it were a pane of clear glass, day and night. The ones from below at night having passed straight through the entire planet without noticing it. They are passing through you right now, trillions every second, and in your entire lifetime only. A tiny handful will ever so much as nudge a single atom of your body. They are the closest thing to nothing that is still something, and every single decaying neutron makes one. Out in the cold of space, a lone neutron flips a quark, sheds a heavy virtual messenger, flings out an electron, and releases one of these ghosts, which then departs into the universe and very likely never interacts with anything again for the rest of time. There is something almost unbearably lonely and beautiful in that image. The neutron's death sends a messenger that no one will ever receive, a faint signal launched into the dark, carrying its small share of energy away forever. Multiply that by the countless neutron decays happening across the cosmos, in every star and every cloud forming matter, and you realize the universe is filled with these silent departing ghosts, a constant invisible exhalation of neutrinos from every transformation of matter, almost none of them ever to be caught. It is worth stepping back to appreciate how much intricate machinery is packed into an event we might have dismissed as a particle simply falling apart. The neutron does not fall apart. It performs an exquisitely choreographed transformation. A quark changes flavor. A handed force acts through a heavy borrowed messenger. Charge is conserved by the ejection of an electron. Energy and spin and momentum are balanced by the release of a near massless ghost. The whole thing obeys the deepest conservation laws of physics with perfect precision, and it does so in an instant, triggered at random after an average wait of 15 minutes, set by the feebleness of the weak force. It is not destruction. It is one of the most elegant and tightly regulated processes in all of nature, hidden inside the smallest and most ordinary of particles. So this is the anatomy of a vanishing, not a destruction but a transformation driven by the one force that can change identity, balanced by a charge carrying electron and an energy-carrying ghost, all set in motion by the flip of a single quark deep inside the particle. It is intricate and precise and strange, and it happens somewhere, countless times every second, in reactors and stars and the upper air, and once, on average, about 15 minutes after any neutron finds itself alone. But we still have not fully answered the central question. We have seen how a neutron decays and why a lone neutron is allowed to. We have not yet looked closely at why the nucleus, in the right circumstances, forbids it, and why in other circumstances it does not. For the protection of the nucleus is more subtle than it first appears, and understanding it takes us into the deepest force of all, the one that digs the valley the neutron hides in. Before we go, carry one image with you. The lone neutron in the instant of its death is not breaking. It is changing. It is one of the building blocks of matter rearranging itself at random, after a patient wait, into a slightly lighter configuration, and announcing that change with a flicker of charge and a whisper of escaping energy. Nothing is lost. Everything is accounted for. The neutron does not end so much as it becomes, and that quiet act of becoming, repeated everywhere matter transforms, is one of the engines that has shaped the universe from its first minutes onward. Hold that gentleness in mind as we turn to the harder question of what holds the neutron back when it is not alone. Let us go there now. We have seen why a lone neutron falls and how it falls. Now we come to the gentler half of the mystery, the half that feels almost protective. Why does the nucleus save the neutron? What is it about being surrounded by other particles that turns a doomed thing into an immortal one? To answer this properly, we have to meet the force that builds the nucleus in the first place, the strongest force in nature. And we have to understand a subtle rule about how particles share space. Start with the obvious problem that a nucleus should not even exist. A nucleus is a tight cluster of protons and neutrons packed into that almost impossibly tiny space at the center of the atom. But protons all carry positive electric charge, and like charges repel. Pack a handful of protons close together, and the electric repulsion between them is ferocious, each one shoving violently against all the others, trying to fly apart. By the logic of electricity alone, a nucleus should blow itself to pieces instantly, and yet nuclei hold together calmly for billions of years. Something must be overpowering that fierce electric repulsion, something even stronger, reaching in to bind the protons and neutrons together against their own desire to scatter. That something is the strong nuclear force, and it is the most powerful force in all of nature. To give a sense of the contrast, the strong force binding the nucleus is roughly 100 times stronger than the electric repulsion trying to tear it apart, and unimaginably stronger than gravity at that scale. It is the firmest grip in physics, the thing that holds the very hearts of atoms together against everything that would scatter them. The strong force is what glues the nucleus together. It acts between protons and neutrons alike, pulling them toward one another with a grip far mightier than the electric repulsion pushing the protons apart. It is, however, a force with a very short reach, unlike gravity or electricity, which stretch out across great distances, growing weaker, but never quite vanishing. The strong force operates only across the tiniest of gaps, essentially only when particles are nearly touching. Within that tiny range, it is overwhelmingly powerful, the strongest thing there is. Beyond it, it falls away to nothing, almost at once. This is why nuclei are so small and so dense. The strong force can only hold particles together if they are crammed right up against each other within its tiny reach. So it pulls the protons and neutrons into a tight, dense knot, where its grip is strong enough to overcome the electric repulsion and bind the whole thing into a stable cluster. And here is the connection to our neutron. When protons and neutrons bind together, under the strong force, they release energy, and the bound cluster ends up in a state of much lower energy than the separate particles would have. We talked about this before as the valley in the energy landscape, and now we can see what digs it. The strong force is the shovel. It pulls the particles into a deep well of binding energy, a configuration so much lower in energy than the separate pieces that the whole nucleus weighs measurably less than its parts would weigh apart. That missing mass, the binding energy, is the depth of the well, and it is the strong force that creates it. The neutron, bound in the nucleus, is sitting at the bottom of a deep well that the strong force has dug, and that depth is part of what protects it. But binding energy alone is not the whole story of the neutron's protection, and this is where it gets genuinely subtle and genuinely beautiful. There is a second ingredient, a rule about how identical particles are allowed to share space, called the exclusion principle. It says that two identical particles of this kind cannot occupy the same quantum state at the same time. Each one must have its own distinct state, its own slot, its own seat. They cannot pile up together into the same condition. They must stack, one per available state, filling the lower slots first and then being forced into higher ones. Now watch what this does inside a nucleus. The protons fill up their available slots, stacking into the lowest energy states they can, one per state, climbing upward as those states fill. The neutrons do the same, separately, filling their own ladder of slots. Now, suppose a neutron in the nucleus wants to decay, to turn into a proton. The new proton it would become cannot just appear anywhere. It has to go into an available proton slot. And if the lower proton slots are already full, occupied by the protons already there, then the new proton would be forced into a higher, more energetic slot, one that is already higher up the ladder. That costs energy, and if it costs more energy than the decay would release, then the decay cannot pay for itself, and it is forbidden. The neutron is blocked, not by the strong force directly, but by the simple fact that there is no cheap room for the proton it would become. All the low-cost rooms are taken. This is the deeper reason a neutron in a stable nucleus cannot decay. It is partly the depth of the binding energy well, and partly this matter of available slots in a stable nucleus. The balance of protons and neutrons is such that turning a neutron into a proton would force that proton into a higher energy state than the neutron currently occupies, making the whole nucleus heavier rather than lighter. And so the decay is energetically forbidden. The neutron is held in place by the geometry of the energy landscape and the rule of one particle per slot. It is safe, not because anything actively protects it, but because every path to a lower energy state has been closed off by its neighbors. The company of the other particles fills the rooms it would need to escape into, and so it stays. Now, I have to be honest with you about an important complication, because the truth is more interesting than a simple rule. And the title of our story is a little bit of a beautiful overstatement. It is not true that a nucleus always saves a neutron. It is not true that being bound always grants immortality. The full truth is that it depends precisely and individually on the energy balance of each particular nucleus. And there are many nuclei in which a bound neutron does decay. These are the unstable radioactive nuclei, and they are all around us. In certain nuclei, the balance of protons and neutrons is off in a particular way, with too many neutrons relative to protons for the most stable arrangement. In those nuclei, turning a neutron into a proton would actually move the whole system to a lower energy state, into a more stable configuration. And so, by exactly the same rule we have been using all along, the decay is allowed, and it happens. A neutron inside such a nucleus undergoes beta decay, just like a free neutron, turning into a proton and emitting an electron and an antineutrino, and the nucleus transmutes into a different element. This is the origin of much of the radioactivity we know. It is bound neutrons decaying inside unstable nuclei, seeking a more stable balance. Carbon used in dating ancient things, certain forms of potassium in your own body, countless medical and industrial isotopes, all of them are nuclei in which bound neutrons are slowly, steadily decaying, because for them the decay leads downhill. So the real rule is not that nuclei save neutrons. The real rule is the one we have had since the beginning, the single rule of energy. A neutron, free or bound, will decay if, and only if doing so leads to a lower energy state, and will be stable if it does not. For a free neutron, decay always leads downhill, because the neutron is slightly too heavy on its own, and so a free neutron always, eventually, decays. For a bound neutron, it depends entirely on the nucleus. In a stable nucleus, the surrounding particles have closed off the downhill path, and the neutron is safe forever. In an unstable nucleus, the path downhill is open, and the neutron decays. The neutron itself is always the same. What changes every time is the energy landscape its neighbors create around it. And this is the true and complete answer to why a neutron cannot exist alone. It is not that the neutron needs company in some vague sense. It is that a neutron by itself is always slightly too heavy, always perched just above a lower state, always free to fall. Only the precise arrangement of a stable nucleus can lift that lower state up out of reach and lock the neutron into permanence. Alone, there is always a way down, and so a lone neutron always, in the end, takes it. Its solitude is its doom, not because solitude is sad, but because solitude leaves the downhill path open, and the universe always, eventually, walks down an open path. Let me give you the simplest possible example of a nucleus saving a neutron, because it makes the whole idea concrete. Take a single proton and a single neutron and bind them together. That little pair is the nucleus of a heavy form of hydrogen called deuterium, and it is perfectly stable. The neutron in it does not decay. Here is a neutron that, set free, would die in 15 minutes, and yet bound to just one proton it becomes immortal. Why? Because binding the two together releases energy and digs a small well, and to turn that bound neutron into a proton would require producing two protons bound together. And two protons bound together is not a stable configuration at all. Their electric repulsion, with no neutron between them to add strong force binding without adding charge, makes that arrangement higher in energy, not lower. So the decay would lead uphill, and it is forbidden. A single proton is enough company to save a neutron forever, simply by closing off the downhill path. The whole grand principle is already visible in the very simplest pairing of two particles. Now contrast that with a famous case where the company is not enough, where the neutron still decays. Take ordinary hydrogen, a lone proton, and add not one but two neutrons to it. That is a form of hydrogen called tritium, and it is unstable. One of its neutrons decays, turning into a proton, and the tritium transforms into a light form of helium, releasing an electron and an antineutrino, with a half-life of about 12 years. Why does the neutron decay here, but not in deuterium? Because in tritium there are two neutrons and only one proton, an imbalance, and turning one neutron into a proton brings the system closer to the balanced, more tightly bound arrangement of two protons and one neutron. The decay leads downhill toward greater stability, and so it happens. Same neutron, different neighbors, different fate. The pattern holds with perfect consistency. It is always the energy balance of the whole system that decides. This is also the deep reason behind something you may have noticed about the heavier elements, that the stable nuclei tend to have more and more neutrons relative to protons as you climb the periodic table. Light stable nuclei often have roughly equal numbers of protons and neutrons, but as nuclei get bigger, the electric repulsion among the growing crowd of protons gets fiercer, because every proton repels every other, and that repulsion reaches across the whole nucleus, while the strong force only binds nearest neighbors. To hold a big nucleus together, You need extra neutrons, which add strong force binding without adding any disruptive charge. They act as a kind of nuclear glue and as spacers, diluting the proton repulsion. So, heavy stable elements carry a surplus of neutrons by necessity. And if a nucleus has too few neutrons, or too many, relative to the sweet spot for its size, it becomes unstable, and it will adjust, often by exactly the kind of neutron decay we have been studying, creeping toward the most stable balance. The stability of every element you know is a story written in this same accounting of protons, neutrons, the strong force, the electric force, and the rule of 1 particle per slot. Let me say a little more about that rule of 1 particle per slot, the exclusion principle, because it is doing quieter work than people realize, and it is genuinely one of the load-bearing pillars of why matter is the way it is. Without it, all the protons in a nucleus would collapse into the single lowest energy state, and all the neutrons too, and the careful structure that makes some nuclei stable and others not would simply not exist. It is the insistence that each particle must have its own distinct state that creates the ladders of slots, the filling from the bottom up, the situation where a new proton might find all the cheap rooms taken. The same principle, acting on electrons, is what gives atoms their structure and gives us the whole periodic table and all of chemistry. So the protection of a bound neutron, the closing off of its downhill path, depends on the very same deep rule that builds the structure of every atom and underlies all of chemistry, and therefore all of life. The neutron hides behind a principle that also wrote the rules for everything you are made of. There is a quiet beauty in seeing how few ideas we have actually needed. The strong force, digging deep wells of binding, the electric force, pushing protons apart, the exclusion principle, stacking particles 1 per slot, and above all, the single rule of energy, the rule that things fall downhill and never climb on their own. From just these, the entire pattern follows. Why deuterium is stable and tritium is not. Why heavy elements need extra neutrons. Why a free neutron dies and a bound one may live forever. The neutron's 2 fates are not arbitrary. They fall out cleanly and inevitably from a handful of the deepest principles in physics, applied with care to each particular situation. Let that settle for a moment against your own body, because it makes the abstraction real. Right now, inside you, there are vast numbers of neutrons bound into the nuclei of the carbon and oxygen and nitrogen and every heavier atom that you are built from. Each of those neutrons set free would die within 15 minutes. But bound where they are in stable nuclei, they have been sitting unchanged for billions of years, since long before the Earth formed, forged in ancient stars, and scattered into space and gathered into the cloud that became our world and eventually became you. You are walking around with countless particles inside you that are individually doomed to die in minutes, if released, and yet have already survived for the entire age of the solar system and far beyond, simply because of the company they keep, the permanence of your own. Matter is borrowed permanence, a stability granted by arrangement, not by nature. Take any one of those neutrons out, and the clock would start ticking at once. Leave it where it is, and it may outlast the Sunday. I find that genuinely moving and worth pausing on before we move to the mystery. We are made of particles that are, in isolation, fragile and fleeting, and that are made enduring only by being held in the right relationships. There is a kind of quiet lesson folded into the physics, one we noticed at the very start, and that has only deepened. Nothing here lasts on its own. The neutron does not, and yet, woven into the right structure, surrounded by the right neighbors, the fleeting becomes the lasting, the doomed becomes the durable, and a particle that could not survive a quarter of an hour alone becomes part of something that endures for eons. Permanence, even at the level of the smallest pieces of matter, is not a thing a particle has. It is a thing a particle is, given by everything around it. We have now understood the neutron's two fates as deeply as the physics allows. We know why it dies alone and lives in good company. We know the machinery of its death and the accounting that governs its life. And so you might think the story is finished, the mystery solved, the neutron fully understood. But it is not, because when physicists try to measure exactly how long a free neutron lives, that simple number we have been quoting, about 15 minutes, they get two different answers. Two of the most careful kinds of experiment ever devised, both measuring the lifetime of the free neutron, disagree with each other by an amount that should be impossible. And no one knows why. We understand the neutron's death in principle beautifully, completely, and yet we cannot agree on how long it takes. That contradiction is where we go next, into one of the real unsolved puzzles of modern physics. Here is where the story turns from settled physics to genuine, present-day mystery. We have spoken all along of a free neutron lasting about 15 minutes. But how do you actually measure that? How do you time the life of a particle you cannot see, that dies at random, that lasts only minutes and then is gone? Physicists have devised two beautiful and completely different ways to do it. Both are masterpieces of careful experiment, and they give two different answers. Answers that disagree by about 9 seconds, by an amount far larger than either experiment's stated uncertainty. This is the neutron lifetime puzzle, and it has stood unresolved for years, and it is real. Let us understand the two methods, because the disagreement only becomes astonishing once you see how each one works. The first method is called the bottle method, and the idea is exactly what it sounds like. You trap a population of free neutrons in a container, a bottle, and you wait, and then you count how many are left. Because neutrons are neutral and slippery and pass through ordinary walls, you cannot just keep them in an ordinary jar. So physicists use very special bottles. They cool the neutrons down to extraordinarily low temperatures, making them move very slowly, so slowly that they are called ultra-cold neutrons, and they hold them using clever combinations of specially coated walls, gravity, and magnetic fields, building a trap that these sluggish neutrons cannot escape. You fill the trap with a known number of ultra-cold neutrons. You wait a measured amount of time, then you count how many neutrons remain. Since the missing ones have decayed, the rate at which they vanish gives you the lifetime directly. You are counting survivors. You are asking, of a trapped population, how many are still here after a known wait? It is, in essence, a careful head count of the living. The second method is called the beam method, and it comes at the same question from the opposite side. Instead of trapping neutrons and counting the survivors, you take a steady beam of free neutrons, a stream of them flowing through a defined region of space, and you count the decays themselves as they happen. Specifically, when a neutron decays, it produces a proton, and you can catch and count those protons. You know how many neutrons are flowing through your measured region, and you count how many protons appear from decays within it. And from the rate at which decay products are produced, you calculate the lifetime. You are not counting survivors, you are counting deaths. You are watching a flowing river of neutrons and tallying how many die in a given stretch. It is, in essence, a careful count of the dying. Two methods. One counts the living, the survivors left in a bottle. The other counts the dying, the decay products appearing in a beam. Both measure the same thing, the average lifetime of a free neutron. In a sane and tidy universe, they would agree. They do not. The bottle method, counting survivors, consistently gives a lifetime of about 877 to 879 seconds. The beam method, counting decays, consistently gives a longer lifetime, about 888 seconds. The difference is roughly 9 seconds. 9 seconds out of about 880. It sounds tiny, a fraction of a percent, but here is why it matters so much. Each method has been refined to a precision far finer than 9 seconds. Each one quotes an uncertainty of only a second or two, sometimes less. So the gap between them is several times larger than the error bars on either side. In the language of physics, the discrepancy is around 4 standard deviations or more, which is the kind of gap that is very unlikely to be a mere statistical fluke. The two methods are not just slightly different, they are saying, each with great confidence, two things that cannot both be true, and they have kept saying it more and more precisely for years as the measurements have improved and the gap has stubbornly refused to close. Sit with how strange this is. We are not talking about a vague or sloppy measurement. We are talking about two of the most precise and carefully controlled experiments in all of physics, performed by brilliant people who have spent careers hunting down every possible source of error, and they disagree clearly and persistently about how long a neutron lives. This is not a comfortable situation. It means that either one of the experiments has a subtle, hidden flaw that no one has yet found, despite enormous effort, or there is something about the neutron itself that we do not understand. Both possibilities are unsettling, and both are taken seriously. Let us consider the first possibility, the one most physicists consider most likely, which is that there is an undiscovered systematic error in one of the methods. A systematic error is not random noise. It is a consistent bias, something that pushes the answer the same way every time, a subtle effect the experimenters have not accounted for. In the bottle method, for instance, if a few neutrons are being lost not to decay but to some other process, perhaps being absorbed into the walls of the trap or escaping in some way not fully accounted for, then the bottle would seem to lose neutrons faster than decay alone would explain, giving a lifetime that is too short. In the beam method, if the count of neutrons in the beam or the count of the protons produced is off by some small consistent factor, the inferred lifetime would be biased. For years, physicists have combed through every such possibility, refining the traps, changing the materials, varying the conditions, cross-checking everything, and still the gap persists. Each method, examined on its own, looks sound, and yet they disagree. And so a second, far more exciting possibility has been seriously proposed, one that would mean the discrepancy is not an error at all, but a discovery. What if the two methods disagree because they are actually measuring slightly different things? Remember, the bottle counts how fast neutrons disappear by any route. The beam counts specifically how fast protons appear. Normally these should be the same because every neutron that disappears should produce a proton. But what if, just occasionally, a neutron disappears without producing a proton? What if, a small fraction of the time, a neutron decays not into a proton and an electron and an antineutrino, but into something else entirely, some other particles that the beam experiment would never count, because no proton appears? This is the dark decay idea, and it is genuinely tantalizing. If a small fraction of neutrons decayed into unseen particles, perhaps into some form of dark matter, the mysterious, invisible substance that seems to make up much of the universe, then the bottle method would see those neutrons vanish, counting them as gone, while the beam method would miss them entirely because they produced no proton to detect. The bottle would measure a shorter lifetime because it sees all the disappearances. The beam would measure a longer one because it sees only the disappearances that make protons. Exact gap between them would tell you how often the neutron takes the hidden, dark path. For a while, this was an electrifying possibility. It suggested that the humble neutron might be a doorway to dark matter, that the answer to one of the deepest mysteries in the universe might be hiding in a 9-second discrepancy in a particle's lifetime. But honesty requires me to tell you where that idea now stands, and the news is sobering. The dark decay hypothesis made specific predictions, and physicists tested if neutrons sometimes decayed into dark matter, there should be certain observable consequences in the laboratory and in the cosmos. For one thing, such decays inside neutron stars would affect how those stars behave, and observations of neutron stars place severe constraints on whether neutrons can take such hidden routes. Dedicated experiments also searched for the specific signatures the simplest dark decay models predicted and did not find them. As a result, the simplest and most exciting versions of the dark decay idea are now strongly disfavored, ruled out, or constrained into small and awkward corners. The neutron probably is not, after all, decaying into dark matter in any simple way. The tantalizing doorway looks, on closer inspection, mostly closed. Let me offer one more way to feel the heart of the disagreement, because it is so clean. Once you see it, imagine you want to know how long the people in a certain town tend to live, and you have two ways to find out. In the first way, you take a large group of newborns and you simply follow them, counting how many are still alive as the years pass, until you can read off the average span from how the group dwindles. In the second way, you do not follow individuals at all. You stand at the town and you count funerals, the rate at which people are dying, and from the death rate and the size of the population, you calculate the average lifespan. In a well-behaved town, these two methods would give the same answer. But suppose they did not. Suppose the follow the group method gave a shorter lifespan than the count the funerals method. What could that mean? It could mean some people in the group are quietly leaving town without dying, so they vanish from your head count but never show up as a funeral. Your survivor count drops too fast and you infer too short a life. That is exactly the shape of the neutron puzzle. The bottle is the head count of survivors. The beam is the count of funerals, the protons that appear. And the bottle gives a shorter life, which would make sense if some neutrons were leaving by a door that produces no proton, no funeral, the beam could count. That is precisely why the dark decay idea was so tempting, and precisely what makes its constraints so important. The actual numbers, refined over many experiments, sit close to where I have said. The most precise bottle measurements, using magnetically trapped ultra-cold neutrons, cluster near 877.5 to 879 seconds. The most precise beam measurements sit near 887 to 888 seconds. Different groups, different countries, different apparatus, and yet within each method the results agree with one another, and between the two methods they stubbornly do not. It is not one rogue experiment against the field. It is two whole families of careful experiments, each internally consistent, pointing at two different numbers. That is what makes it so hard to wave away. If it were a single odd result, you would suspect that one experiment. But the bottle results agree with other bottle results, and the beam results agree with other beam results, and the two camps simply will not meet. The disagreement is structural, tied to the method itself, which is exactly why it has been so maddening and so fascinating, and why it points so cleanly, if it points anywhere, at some difference between counting the living, counting the dead, which leaves us, honestly, with a genuine, open, unresolved puzzle. The most exciting explanation has largely been ruled out. the mundane explanation, a hidden systematic error, has been hunted relentlessly and not found. And so the discrepancy simply sits there, 9 seconds wide, a small but stubborn crack in our knowledge of one of the most basic particles in nature. Physicists continue to attack it from both sides, building new and more precise experiments, refining the old ones, cross-checking, searching for the flaw or the new physics that must be there somewhere. New measurements keep coming. The gap keeps, for now, refusing to fully close. It remains one of those rare and wonderful situations in science where a simple, basic, seemingly settled question, how long does a neutron live, turns out to have an answer we cannot yet pin down. It is worth understanding why physicists care so much about pinning this number down to the last fraction of a second, because the precision might otherwise seem obsessive. The lifetime of the free neutron is not just a fact about one particle. It is a key input into some of the deepest equations in physics. The rate at which a neutron decays is directly tied to the fundamental strength of the weak force, and to a quantity that describes how readily one kind of quark turns into another. Measure the neutron lifetime precisely enough, and you are effectively measuring a basic constant of nature, one that feeds into rigorous tests of our entire theory of particles, the framework physicists call the Standard Model. If that framework has any hidden cracks, any place where new physics is lurking, a precise neutron lifetime is one of the sensitive probes that might reveal it. So the chase after those last few seconds is not pedantry. It is one of the ways we test whether our deepest theory of matter is complete. A discrepancy of 9 seconds in this context is not a rounding error to be shrugged off. It is potentially a signpost, either toward a subtle experimental effect worth understanding, or toward physics we do not yet have. It is also worth feeling the sheer difficulty of these measurements, because it deepens the respect the puzzle deserves. Consider the bottle experiments. You are trying to hold onto particles that pass through most matter, that carry no charge to grab onto, that you can only contain by chilling them until they crawl, and then catching them with coated walls and magnetic fields and the gentle help of gravity. And you have to be certain that every neutron that goes missing went missing by decaying and not by slipping through a wall or being absorbed or finding some other quiet exit. Every possible leak has to be understood and accounted for to better than a part in 1,000. Or consider the beam experiments. You have to know exactly how many neutrons are passing through your measured region at every moment, and you have to catch and count the faint trickle of protons produced by decays, protons that emerge with very little energy and are easy to lose. Both measurements push the art of experiment to its very limits. The fact that they can be done at all is astonishing. The fact that they have been done well enough to reveal a real, statistically significant disagreement is a genuine triumph, even though the disagreement itself is a headache, and the disagreement has a history worth knowing because it did not appear all at once. For a long time, the uncertainties on both kinds of measurement were large. enough that they overlapped, and there was no clear conflict. The lifetime was known to within a range, and bottle and beam results both fell inside it, and all seemed well. But as both methods improved over the years, as the error bars shrank, the two central values did not converge toward each other the way you would hope. Instead, they held their ground, and the shrinking uncertainties pulled them apart until the gap between them became too large to dismiss. It was the very improvement of the experiments, the heroic reduction of their errors, that turned a comfortable agreement into a glaring contradiction. The better we measured, the worse the problem looked. That is often how the most important puzzles announce themselves, not with a dramatic new result, but with an old discrepancy that simply refuses to go away as the precision climbs. There is a particular discipline in how physicists have handled this, and it is worth admiring. Nobody has rushed to declare new physics. Nobody has thrown out either method. The community has, by and large, held both results in view at once, treated the disagreement as real, and kept working, building new experiments designed specifically to settle it, including approaches that try to measure the lifetime in entirely new ways to break the deadlock. This is science behaving exactly as it should in the face of a genuine anomaly. Not denial, not premature excitement, but patient, stubborn, honest investigation. The puzzle is held openly as a puzzle. The possible explanations are weighed soberly, and the work goes on year after year, because the question is worth answering, and the answer has not yet come. I find something deeply heartening in that, not frustrating. It is a reminder that even now, even at the foundations, even with the most ordinary particles, the universe still holds secrets we have not cracked. The neutron lifetime puzzle is not a sign that physics is broken. It is a sign that physics is alive, that there is still real work to do, real mysteries, hiding in plain sight, in something as humble as the ticking clock of a lonely neutron. And whatever the resolution turns out to be, a subtle error finally caught, or some genuinely new physics nobody has yet imagined, finding it will teach us something. The 9 seconds are a door we have not yet opened. We are still standing in front of it, keys in hand, trying each one. And there is something beautiful about a universe that still makes us work that hard to understand its simplest pieces. We began with a single neutron and a ticking clock. We have followed it down into the nature of mass and energy, into the machinery of its decay, into the shelter of the nucleus, and into a genuine unsolved puzzle. Now let us widen all the way out to the largest possible view and ask why any of this should matter beyond the curiosity of it. Because the short life of a lonely neutron, it turns out, is woven into the history of everything that exists, including you. Go back to the very beginning, to the first minutes after the Big Bang. In that unimaginably hot, dense moment, the universe was a seething soup of fundamental particles, far too hot for atoms or even nuclei to hold together. And in that soup, protons and neutrons existed in roughly equal numbers, constantly transforming back and forth. into one another under the extreme conditions. As the universe expanded and cooled, those transformations slowed and then largely stopped, leaving a certain mix of protons and neutrons frozen in. And then a race began, a race against the clock we have been studying all along. Here is the race. As the young universe cooled, the free neutrons in that soup faced their usual fate. On their own, they would decay, each one with that same 15-minute average life. But there was another possibility. If a neutron could find a proton and bind to it before it decayed, and then gather into a nucleus, it would be saved, locked into the shelter of binding before its clock ran out. So in those first minutes, there was a genuine race between neutron decay on one side and nuclear fusion on the other. Every neutron was running down its 15-minute clock, and the question was whether the universe could cool to the point where nuclei could form and capture those neutrons before too. Many of them decayed away. This race set the chemical composition of the entire universe. The neutrons that were captured in time ended up bound mostly into helium, which needs 2 neutrons and 2 protons. The protons that were left over, with no neutron to pair with, remained as bare single protons, which is to say, as hydrogen. And because the neutron lifetime is what it is, about 15 minutes, a certain fraction of neutrons decayed before they could be captured, shifting the final balance. The result worked out in those first few minutes of cosmic history was a universe made of roughly 3/4 hydrogen and 1/4 helium by mass, with traces of a few light elements. And that ratio, set by the race between fusion and the neutron's clock, is very nearly what we still observe in the universe today. The oldest, most pristine matter we can find has almost exactly that composition. It is one of the great confirmations of our understanding of the Big Bang. Now feel what that means. If the neutron lifetime was significantly different, the outcome of that primordial race would have been different, and the universe would have a different mix of elements. If neutrons decayed much faster, almost all of them would have vanished before they could be captured, leaving a universe of nearly pure hydrogen with little helium and a very different path for the first stars. If neutrons lived much longer, far more of them would have survived to be bound, and the universe would have locked up much more of its matter into helium and beyond, leaving less hydrogen. The 15-minute lifetime is not an arbitrary detail. It is one of the numbers that tuned the raw composition of the cosmos, the starting material from which all stars, all planets, all chemistry, and all life would later be built. The hydrogen that fuels the stars and forms the water in your body, the helium, the balance of the light elements, all of it traces back in part to how long a lonely neutron survives. The clock we have been watching helped set the ingredients of everything. So the precise value of the neutron lifetime, the very number that 2 experiments cannot agree on, is not a trivial quantity. It is stitched into the foundations of the universe. This is yet another reason physicists care so much about closing that 9. Second gap. The neutron lifetime is an input into our calculations of how the early universe made its elements, and a more precise value sharpens our understanding of those first crucial minutes. The lonely neutron's clock is quite literally one of the dials that was set at the dawn of time. Let us turn to another place where neutrons live strange lives, because it deepens the theme that has been running underneath this whole story. We have said that a free neutron decays and a nucleus can save it. But there is one more way to save a neutron, and it is among the most extreme objects in the universe, a neutron star. When a massive star dies and its core collapses, gravity can crush matter so violently that protons and electrons are forced together into neutrons, and the entire core becomes a single, almost unimaginably dense ball of neutrons, a city-sized object containing more mass than the sun, made overwhelmingly of neutrons packed shoulder to shoulder. And here is the wonderful thing. In a neutron star, the neutrons do not decay, even though they are not bound into ordinary nuclei. They are saved by a different mechanism entirely. The crushing gravity and the sheer density pack the would-be decay products so tightly that there is, once again, no available low-energy state for a new proton and electron to occupy. Every slot is full. The downhill path is closed, not by the binding of a small nucleus, but by the overwhelming crowding of an entire collapsed star. The neutron is stabilized by gravity itself. Think about what that tells us. A neutron can be saved by the company of a single proton, as in deuterium. It can be saved by the arrangement of a stable nucleus, and it can be saved by the crushing gravity of a dying star, which packs matter so densely that decay is forbidden across an entire object the size of a city. In every case, the principle is the same. The neutron is stabilized not by anything within itself, but by its surroundings closing off the path to a lower energy state. From the smallest pairing of two particles to the most extreme object in the cosmos, the rule holds. Stability is conferred from outside. Permanence is a gift of arrangement. And this, I think, is the quiet truth at the heart of our whole story, the thread we first noticed at the very beginning and have followed all the way through. We tend to imagine that things either last or do not by their own nature. That permanence is something a thing possesses on its own. The neutron tells us this is not so. The very same particle is fleeting in isolation and eternal in the right company, and nothing about the particle itself ever changes. Its endurance is entirely a matter of relationship, of what surrounds it, of the landscape its neighbors create. Alone, it cannot last. Held in the right structure, it can outlast stars. The neutron does not carry its fate within it. Its fate is written by everything around it. There is something in that worth carrying out of physics and into the rest of life, if you are inclined to let it travel. The neutron is a reminder that lasting is not usually a solitary achievement, that the things which endure tend to do so because they are held, supported, bound into something larger than themselves. That isolation is, for many, Things in this universe, a kind of slow undoing, and that belonging, connection, the right surroundings are what grant the gift of permanence. The lonely neutron cannot survive its loneliness, and neither perhaps can a great many things. There is no need to push the metaphor too hard, but it is there, written into the most basic physics, that to be held is to be saved. Let me add a little more texture to that primordial race, because the details are lovely, and they show how delicate the whole thing was. You might think that as soon as the universe was cool enough, neutrons and protons would simply snap together into nuclei, and the neutrons would be safe. But there was a bottleneck. The very first step, binding a single proton and a single neutron into deuterium, is a relatively fragile union, and in the intense bath of high-energy radiation that filled the early universe, those first deuterium nuclei were blasted apart almost as fast as they formed, until the universe cooled below a certain point. Deuterium could not survive, and without that first step, path to helium was blocked. So the neutrons had to wait, running down their clocks, while the universe cooled to the point where deuterium could finally hold together. This delay is sometimes called the deuterium bottleneck, and during it, neutrons were quietly decaying, thinning out, losing the race one by one. Only when the bottleneck cleared could the surviving neutrons rush into helium. The final helium abundance depended on exactly how many neutrons were left when that moment came, which depended on how long the bottleneck lasted, which depended on the neutron lifetime. Everything was interlocked. A different neutron clock and a different universe of elements. There is a thought that often arises here, and it is worth voicing carefully. The neutron lifetime is one of a number of physical quantities that, had they been substantially different, would have produced a universe far less hospitable to complexity and to life. A universe of nearly pure hydrogen, or one that locked almost all its matter into helium, and heavier elements early on, would have made very different stars, and perhaps a very different chemistry, possibly one in which beings like us could never arise. Some people find in this a sense of fine-tuning, a feeling that the constants of nature sit suspiciously well placed for our existence. Others see it as simply the way things are, with no deeper intention, a universe that happens to have these values and living things, that happen to have arisen within the possibilities they allow. I will not try to settle that question, because it reaches beyond physics into matters where honest people disagree. But I will say that the neutron lifetime is one of those numbers that sits in the conversation, one of the dials whose setting shaped a universe in which, eventually, something could wake up and wonder about neutrons at all. Let me also return to the neutron star for a moment, because it connects to one more beautiful piece of physics worth naming. The reason the neutrons in a neutron star resist further collapse, the reason such a star does not simply keep shrinking into nothing, is a pressure that does not come from heat at all. It comes from that same rule of one particle per slot, the exclusion principle. When neutrons are packed unimaginably close, the principle forbids them from all crowding into the same low energy states, and, forcing them together, pushes them into higher and higher energy states, which resist the compression. This resistance, born purely from the refusal of identical particles to share a state, creates a pressure strong enough to hold up an entire collapsed star against its own crushing gravity. It is the same principle that stacks protons and neutrons in ordinary nuclei, the same principle that closes off the neutron's decay path, now operating on the scale of a whole star, holding a city-sized ball of neutrons stable against gravity. The same quiet rule that protects a bound neutron from decay also holds up the densest stars in the universe. There is a deep unity in that, the same handful of principles echoing from the smallest scales to the largest, and it is worth dwelling just a little longer on how strange and wonderful it is that a neutron star exists at all. Here is an entire object, more massive than the Sun, compressed into a sphere just a few kilometers across, made almost entirely of the very particle we have been calling doomed. A free neutron dies in 15 minutes. Gather an unthinkable number of them, crush them together with the gravity of a collapsed star, and they become stable, holding firm for as long as the star endures, which can be billions of years. The most fragile particle, assembled in vast enough numbers under extreme enough conditions, becomes one of the most durable structures in the cosmos. It is the deuterium lesson written enormous. Company saves the neutron, whether the company is a single proton or a whole star pressing in from every side. The principle does not care about scale. It only cares whether the path downhill is open or closed. I want to gather the two great threads of this story together before we close, because they belong together. The first thread is understanding how completely we grasp the neutron's two fates, the elegant accounting of mass and energy, the machinery of the weak force, the shelter of binding, the rule of one particle per slot. By that thread, the neutron is one of the best understood objects in all of science, its life and death, explained from the deepest principles with beautiful precision. And the second thread is mystery, the stubborn 9-second gap, the two careful clocks that will not agree, the open question of exactly how long the lonely particle survives. By that thread, the neutron still eludes us, still keeps a secret, and both threads are true at once. We understand the neutron deeply, and we cannot fully measure it. That combination of profound understanding shot through with genuine unsolved mystery is what real science actually looks like. Not a finished story, a living one. There is a humility in holding both at once, and I think it is the right posture to carry. Away. We can be proud of how much we know, that we can trace the death of a particle down to a flipping quark and a borrowed messenger and a balanced ledger of energy. And we can be honest about what we do not know, that a simple question, how long does a neutron live, still has an answer we are chasing. The universe rewards our understanding generously, and it also keeps a few cards face down, even in its simplest hands, to keep us honest and to keep us looking, and the looking itself is a kind of gift. Somewhere right now, in a laboratory, physicists are cooling neutrons until they crawl, trapping them in bottles, counting survivors. Elsewhere, others are flowing neutrons through beams, counting the faint protons of their deaths. They are trying patiently to close a gap of 9 seconds in the life of the first, most ordinary of particles, because they believe the universe should make sense, and because the place where it does not quite make sense is exactly the place where something new may be waiting. That refusal to look away from a small, persistent discrepancy is among the finest things our species does. The lonely neutron called it forth. Its ticking clock set them to work, and they have not stopped. So let us return at the very end to where we began, to a single neutron floating alone in empty space with a clock ticking beside it. When we started, it was just a strange fact, a particle with an inexplicable deadline. Now look at it again, knowing everything we know. That ticking is the slow rarity of the weak force, waiting to flip a single quark. That deadline exists because the neutron is, by the barest sliver of mass, too heavy to be left alone, perched above a lower state with a path leading down. The transformation, when it comes, will be an exquisitely balanced act of becoming, sending a proton, an electron, and a ghostly neutrino out into the world. And the exact length of those 15 minutes is a number woven into the birth of the elements, and still, to this day, not fully pinned down, the subject of a real and living mystery. That lonely neutron, which cannot survive its solitude, is one of the building blocks of you and of the stars and of the early universe, and it carries in its brief life some of the deepest principles in all of physics, and one genuine unsolved puzzle and a quiet lesson about what it takes to last. Its 15 minutes are not empty waiting. They are full of meaning if you know how to look. And now, perhaps you do. It is a small thing, a neutron, almost nothing at all, a speck within a speck at the very bottom of the scale of matter. And yet we have found in it the nature of mass and energy, the rarest of the forces, the origin of the elements, the stability of stars, a real unsolved riddle, and a quiet truth about what it takes to endure. The smallest things, looked at closely enough, are never small. They open onto everything. The clock is still ticking, somewhere, on countless lonely neutrons across the universe, each one living out its brief, bright span, each one in its vanishing, helping to make the fide world. Let that be the thought you carry away into the quiet. Nothing lasts entirely alone, and there is a strange grace in that, written all the way down into the smallest pieces of everything there is.